All right, welcome back. We are going to briefly talk about compound interest now. And so, if we're looking for when we're looking at compound interest, we're now talking about new interest being calculated on principal plus interest earned. All right, so we're looking up here for each new period. So when we talk about compounding, there is a point in time. After a certain duration of time, we compound interest. In other words, we take interest anew on whatever has been earned up until that point. So we can compound annually, quarterly, monthly, daily, all sorts of options. And depending on how we do that will change exactly what the value of our money is. So new interest, again, is credited at the end of these predetermined periods, our compounding period. So we're going to demonstrate compound interest via an example and then develop our formula from there. So let's compare simple and annual compound interest for a $1,000 deposit at 2% interest for 5 years. So I'm going to briefly shuffle over to the Excel workbook, and let's look at our updated simple interest. So $1,000 at a 2% annual interest rate for 5 years should earn us $20 in interest 5 years, right? 5 different times. So total, we would have a future value of $1,100. Sounds good. Now with compound interest, year one, if we say we're compounding annually, year one, our beginning amount is again $1,000, and the interest earned during that period is 20% of that, or pardon me, 2% of that, which is $20. So at the end of year one, there's no difference between simple and compound interest because we haven't actually compounded yet. Now we put like a line here and we compound interest, which means during year two, our new beginning amount, all right, our beginning amount is $1,020, and that is what interest is calculated based on. All right, no longer is it calculated on the original 1,000 like simple interest. It's now computed based on the beginning amount of our new period. So during that period, we earn 2% of that amount. All right. And then because it's yearly, we earn that full 2%. Right? And then the balance at the end of the period is just adding the interest earned plus whatever we began with. And then now as we begin the third period, we compound again. So interest will be taken again based on our new total. And so as we continue this, right, we see that at the end of 5 years, simply compounding once a year, all right, we earn an extra $4.08 approximately relative compared to simple interest. All right, so and the more times we compound, assuming we're not withdrawing any money, the greater that difference will be. In other words, we'll earn interest on a higher number each time we compound. All right, so here I've denoted a few variables to stand for some basic things in terms of principal, annual interest rate. That's going to be key here. Annual interest rate. All right, the number of periods per year. All right, and then the total number of periods in terms of M, which M is then really equal to N times R. Right, if we think about that, pause it and make sure you understand that. So in general, all right, compound interest looks like this. The first period, we start with the principal. We earn the principal times, now not just times the rate, right, because that rate is an annual rate. It's times the rate divided by how much of the year we get. So divided by how many times we're compounding each year. All right, and so the ending amount is just adding a plus sign between these two things. All right, and then I factor the P out. That's common for us to factor the P out. All right, so P plus P times R over N is equal to our ending amount. And then at year two, now this right here, this ending amount of year one, or instead of year, I'll say period one, this, all right, becomes our new beginning amount. And then we earn interest on that. So this beginning amount is multiplied by our rate, again, split up depending on how many times per year we're compounding. Right? So if we're compounding 12 times per year, the annual interest rate needs to be divided by 12. Right? And then again, now we can factor this term out of our sum, all right? And we've got 2 of these factors squared, right? Because, well, let's make sure we see why that is. All right. So if we add these 2 things together, all right, if we put a plus sign between them, all right, I've now got a term with this factor and a term with this factor. So as I factor p times 1 plus r over n out, we get a 1 from this factor over here and a r over n from this factor. So we really have something that looks like equals p times 1 plus r over n is what we factored out, and then we're now multiplying by what is left over from our factor. So I'm going to straighten that out a little bit. So this first chunk is what was factored out, and now the 1 comes from, we need to multiply this thing back in by 1 to get this, and the r over n is from this factor. So we really just get a second factor of the 1 plus r over n quantity, and so we will square it. And we continue that every period, all right? We now start with a new beginning amount, and we get a new factor of 1 plus r over n every time we compound. And so if we compound m times totally, which remember, that is just equal to n times t, right? The number of times compounding per year times the number of years, right? We will get exactly what our formula is for compound interest right here, right? So this, I've just drawn a line here to say the future value of compound interest, all right, is simply equal to, right, this p times the quantity 1 plus r over n, that whole quantity raised to the mth power or raised to the n times tth power is how I'll typically write it. All right, and so this question, can you write it in terms of n and t as well? Yeah, we just did that. We just talked about it. In other words, instead of writing to the mth power, and then we would write it to n times t as our exponent. So notice I'm putting in parentheses everything that goes in the exponent, all right? Because superscript doesn't work well with my PDF editor. All right, so we're good. So that's future value for compound interest. And present value would be then solving in a similar way as what we did before in terms of dividing through to solve for p, for example. All right, I want to make one comment about future value for continuous compound interest, because this is going to come into play with inflation. So a good discussion question / brownie point objective would be to research Euler's number E. In other words, it's approximately 2.7129, I believe, something never ends. And bonus points in terms of if you can explain why it shows up here. All right, but if we're looking for continuous compound interest, which we'll explain again why we care about that in inflation. In other words, not just compounding 365 days a year or times a year, but always compounding, never stopping, never ceasing, continuously compounding. All right, then that future value is simply equal to P times E raised to the RT. Now, only E is raised to the R times Tth power, where R is, again, our annual interest rate, and T is the number of years. So that's PERT, right? PE to the RT. Maybe you've seen that before. So we'll come back to that. We won't need this for the next example, but we'll come back to that. So example 5 is really quite important, and so I want to give you all the chances to work through this on your own, because it really hammers home the difference between simple and compound interest. So you're going to compare the results at age 65 for 2 retirement plans. Plan A for Angie and Plan B for Barry. So Angie begins saving at age 20, deposits $2,000 every year, starting on her 21st birthday is her first deposit, and on her 30th birthday is her last deposit. So there should be 10 deposits there. But then never contributes again. And Barry doesn't start until age 30 and then deposits $2,000 every year from 31 to 65. again on his birthday. So 35 deposits there. All right. So I'm asking you to construct a table in Excel to compare the two plans. I've actually constructed the table for you, and we're going to look at it in a second. But I want to make a comment that an 8% annual interest rate throughout that length of time would require probably a fairly aggressive investment portfolio. Just a side note. But let's take a look at our Excel folder in the second tab. This is here a worked out example of simple interest and compound interest. I encourage you to play around with it, get used to changing things up. For example, here's 12, right, times compounding per year. You can do all that sort of neat stuff. But example 5 and the following right here are all going to be in this next Excel sheet. So here I have the rate, an interest rate. I have the age of both Angie and Benji, or whoever the B name was. All right, and in account for Angie, I've got $2,000 deposited the first year, and then notice the second year she's got $2,000 deposited plus the interest earned over that first year plus the new money deposited. Right? So in other words, if you look in the formula here, this last $2,000 that's the amount she's putting in on her 22nd birthday. And now notice if you go down to her 31st birthday, all right, that stops. She's no longer depositing money, all right, on her 31st birthday, but she's still earning some interest, right? And so a good question is, can you figure out exactly where this data is coming from? In other words, where these values are coming from. And they're coming from compound interest formula. All right, and see if you can piece together how I constructed this Excel sheet, or can you construct a better one? Because I think there's arguably a better way to even arrange this. And over here we've got the second account. And so I just want to hammer home a note. You've got some stuff to do in terms of 3 problems for me for next week in terms of simple and compound interest. But right here is pretty important. All right, so before account B has deposited any money, all right, the year before in Angie's account, she has already accumulated $28,000, all right, on that birthday when she makes her last deposit, right, over that course of 10 years. Okay, via compound interest. And now as we continue on, all right, a good discussion question would be, will account B ever catch account A? Because we see at 65, right, Angie is clearly making more, or is clearly has more. Well, if you notice, a really neat thing to note is how much she makes from interest versus how much this individual makes from interest and his deposit. All right, and so do we expect these two graphs, these two curves, ever to cross? Because they are curves, they are not lines, they are actually exponential curves. So here's this example. As you work through it, try to make sure you understand exactly where we're coming from. That's all really for compound interest. We're going to come back and talk about inflation in a little bit. There are examples 6 and 7 I'm going to go through on this sheet. Examples 8 and 9 I'm not going to cover in a video, but they're really good examples based on consumer credit. And I'll mention them again at the end of next video. But I encourage you to look through those and familiarize yourself with some different types of consumer credit. The moral of the story for compound interest or interest altogether is start saving now. Please, for goodness sake, help yourselves out. Start saving now. All right, I'll see you back here for inflation.